Welcome to Frequency Matters, the RF and Microwave Update Series. I'm Pat Hindle, and I'm here with Jerome Patoux, Director of Marketing, Aerospace and Defense at Analog Devices. Welcome, Jerome.
Hello, Pat. It is good to see you. Thank you for having me. It's great to be here and be part of this conversation.
Yeah, so today I thought we would discuss radar technology and how that might evolve in the future. So Jerome, why does radar technology need to evolve, and how does that influence new electronic technologies?
Well, that's a good question to start with. So in aerospace and defense, any evolution is typically linked to limitations of previously used technologies, whether it is to new threats or to new applications. In the case of radar, it's a bit of both. On one hand, the evolution of radars is driven by the necessity to detect more sophisticated threats and respond quickly. Among those new threats that are emerging, you can find, for example, small targets like drones or drone swarms, hypersonic targets, stealth fighters that have become smarter in avoiding detections. And the evolution of radar is also fueled by the need to support advances in non-military application as well, in areas such as weather formation monitoring, collision avoidance, autonomous cars, or air traffic control, for instance. All these radar applications require continuous evolution of advanced technologies, advanced capabilities, so they can essentially continue to help protect life or to help improve quality of life. So back to your point on how these evolutions influence new technologies. AESA radar, which stands for Active Electronically Scanned Array Radars, continue to evolve to larger and more complex arrays. They use multi-beams that can be simultaneously steered in multiple directions at the same time without moving an antenna. They offer a higher resistance to jamming and form the basis of 3D radars by providing the location of the target, its speeds, and more accurate distinction of the targets. So, for example, distinguishing a bird from a drone. There is a continual need for performance, greater range and resolution, lower detection thresholds, precise spatial envelope control, multiple frequency band coverage, and mission convergence. These needs drive more advanced electronics and disruptive technologies. Analog Devices is at the center of innovation in all areas supporting these evolutions. We do that by leveraging smart high-frequency digitizers with hardened but flexible DSP capabilities, high-performance RF 2-bit solutions, platforms for precise calibration and synchronization of multiple channels in beamforming implementation, as well as power-efficient advanced GaN amplifiers and the ability to integrate on chip, in package, and in modules. In addition, software-defined capabilities allow mission convergence. So you can have one set of hardware being software adjusted to multiple missions. Lastly, we even offer rad-hard versions of complex integrated solutions for designs of radar systems going to space. These include, for example, beamformers, high-speed digitizers, transceivers. So staying ahead of sophisticated threats, reducing SWaP-C, which stands for size, weight, and power and cost, and facilitating the adoption of new disruptive technologies are all challenges recognized at ADI today. And we constantly invest in innovative ways to help our customers increase the capabilities of their radar systems.
Yeah, ADI really does a lot in the system chain. They do it from antenna to bits, so there's a lot of content to add there. So where do you see phased array architectures evolving in radar applications in the future?
So what we tend to see at our customers is that a combination of analog and digital beamforming is the most popular architecture used today for their system-level architecture. Full digital beamforming has some advantages, and its adoption will likely accelerate in AESA radars, especially now with ongoing advancement in RF component integration. However, the chosen beamforming technology really depends on a set of trade-offs to a particular mission profile. Terrestrial radar, for example, and airborne radars have very different constraints related to the adoption of beamforming technology, whether it is analog or digital beamforming. But whether the application requires analog beamforming, digital beamforming, or even hybrid beamforming, analog devices has been investing R&D dollars in technologies that are that support all combinations. Also, direct sampling architecture at L and S bands can be realized today with available RF sampling converters, and we are also moving to direct sampling at higher frequency bands. So our phased array technology can enable smart radio partitioning and relevant integration, so our customer can reduce swap-C and get to market faster, basically. On a similar note, ADI provides enablement platforms for phased array technologies, such as the Quad-MXFE phased array platform for S and L bands, and also the X-band development platform. These platforms support customer in the fast adoption and validation of subsystem architecture, so they can quickly integrate new technologies into a real system solution. Customer can also develop their own proprietary IPs and quickly validate them on a development platform, so they can reduce the development time, development effort, the time to market, basically, and also ease the design of the final products. Lastly, another evolution in phased array radars comprises of more processing power at the edge. So especially in larger array implementations, where the number of beams increases and drives the needs for more processing power, and also because of the push for digital beamforming implementation, where we need some processing after each element.
You mentioned different types of phased array beamforming technologies at the system level. How are systems designers making the trade-offs between analog, digital, and hybrid beamforming?
And so transmit receive modules or TR modules are located behind each antenna element, and analog beamformers are placed behind the TR modules. So the analog beamformer combines all the elements to a centralized receiver channels. Therefore, analog beamforming reduces the number of channels to be digitized. So this usually leads to the lowest power consumption, but they have the most complicating RF routing task. This limits the practical number of beams that can be supported. This is, however, a very attractive option for power-limited application in contested spectrum scenarios. And to give you some example of good beamformers, the ADR 3000 and the ADR 3001 are recent beamformer ICs in the context of analog beamforming. They are ADI's latest BiCMOS highly integrated beamformer for SATCOM, and they offer multi-beam operation, fast beam hopping, and they're also very low power consumption with less than 12 milliwatt per channel. In digital beamforming now, the beams are created in the digital domain. Precise calibration and synchronization are required between channels, and supporting higher boundaries typically requires more sophisticated digitizers, and usually that leads to higher power consumption. However, digital beamforming offers an excellent beam control and the simplest RF routing. Many more beams can be supported and can be steered simultaneously, which makes it a very attractive architecture for high data payload applications. We can realize digital beamforming today using ADI's highly integrated digitizers, such as the MXFE family, AD908X, and ADI development platforms can help with challenges related to calibration and synchronization of multiple channels in digital beamforming implementation. Finally, for hybrid beamforming, there is a converter behind a group of elements that we call a subarray, resulting in a most acceptable trade-off between the pure analog case and the pure digital case regarding power, broad real estate and processing capabilities, especially in large array implementations. So while Analog Devices is investing in the future of digital beamforming, we are equally committed to investing in integrated beamformers, analog beamformers, in order to support our customer with the technologies to realize a system beamforming architecture needed for their mission profile.
So phased arrays have traditionally been made up of TR modules. With the proliferation of the flat panel arrays for 5G and satellite applications, do you see the radar evolving that way?
5G communications and radar technology have a different system requirement, but the progress we have seen in the beamforming techniques in communications are also seen in radar when moving to flat panel implementations. Historically, TR modules were multi-technology with perhaps a pin diode switches, ferrite-based phase shifter, gas amplifiers, and silicon controllers. This forced a large form factor whose cross-section still had to fit within the lattice spacing of the array. More recently, as a circuit element were able to be implemented on a monolithic piece of silicon, one beamformer IC with integrated amplifiers can serve multiple elements in a flat panel at K-band today. Even in cases requiring gas or GaN TR modules, today we can have four modules and one beamformer IC fitting into an X-band lattice. For example, four ADI ADTR1107 TR modules and one ADAR 1000 beamformer are used on ADI's latest X-band development platform.
So you mentioned GaN technology. How is GaN affecting the architecture and packaging configurations of phased arrays?
So given the restriction on lattice spacing in radar to be half wavelengths, solid-state GaN solutions are enabling high-power AESA. This put pressure, of course, on packaging solutions and cooling techniques to get the power out of the antenna. And ideally, this would be a simple PCB with no heat sinking. The efficiency, reliability, and power density of GaN amplifiers have made it an attractive replacement for TWT amplifiers, which would have been way too large physically for AESA technology. There is a continued focus on to make the GaN PAs more efficient to generate less heat, like with new process technology, embedded heat sinking technologies within the PCB, and extracting heat in various ways. There are higher thermally conductive materials in development today that would allow the customers to adopt an SMT solution that would most likely be preferred. So ADI is investing in GaN. ADI now has a fast-growing portfolio of GaN amplifiers that support an array of applications across radar, of course, but also electronic warfare. And as a matter of fact, ADI recently released high-power, high-efficiency C, S, and X-band GaN PAs, which help enable high-performance AESA radars.
Well, it's great to hear that Analog Devices is investing in the evolution of radar technology. And Jerome, really appreciate your insights in the analog and digital beamforming and the trade-offs of both architectures. It's very interesting to learn about the latest technology from ADI, such as the single chip analog beamformer ICs, monolithic high performance digitizer solutions with the enhanced DSP's capabilities, and single package transmit and receive modules that enable high performance integrated architectures. ADI is kind of unique in offering that complete antenna to bit solution, and they're really at the forefront of radar technology that will help manufacturers attain their SWaP-C challenges. So thank you again for being with me today, and thank you to our audience for watching Frequency Matters.